If you wonder what you need to achieve to make your cluster safe and reliable, then this episode is for you. Welcome back to the Is It Observable YouTube channel. Today's episode is part of the Kubernetes series where we covered lots of various topics. Today's episode, we focus on explaining what are the crucial tasks that we need to implement to provide a secure Kubernetes cluster. We'll cover all the security best practices on Kubernetes from the build to deploy to the runtime of our workload. This episode will be followed by several episodes presenting solutions that will be used to secure our Kubernetes environment. If you enjoyed today's content, don't forget to like and subscribe to the channel. So let's see what we're going to learn from this episode. We'll start by a small introduction explaining how a hacker could take control of our cluster. We will then cover specific topics to secure each layer of our environment, starting with building secure applications and containers. Then we will look at limiting the permission to our workload. Of course, we will look at controlling and limiting the network within our cluster, limiting the resource usage in case of DDoS attack. And last, we will look at the value of using runtime vulnerability scanners or security toolings that you can use at the runtime to detect suspicious events. When utilizing cloud-native technologies such as Kubernetes, we often forget crucial security best practices. Sometimes, we often think that Kubernetes will provide out-of-the-box security. Well, it's a bit wrong. At the end, a hacker is a bit like a thief that wants to break into our house or apartments to take our most precious items. Similar to our house, the hacker will try to find a way to enter in our house by unlocking our door, breaking our windows. In the Kubernetes world, the door or window would be the assets that we expose to the outside world. So what do we expose out of the cluster? Well, we know it. So first, the application through an ingress rule, gateway API, service mesh, various ways of exposing applications, the actual Kubernetes API to deploy and look at our resources. It would then mean that we will try to put the right locks or protections to our network assets by just using, for example, SSL, MTLS, and of course, the right level of applications to our Kubernetes API. And then we have our actual application that could also expose vulnerabilities. Application vulnerabilities could be resolved by applying security best practices when coding our application, avoiding SQL or command line injections. But even if we have done all the best coding practices, if we are using a library that has a well-known vulnerability, then the attacker could also try to take advantage of it. Similar to our house, even if we use the best locks, doors, alarms, a talented thief would be able to penetrate our house. So it means that we need to make their journey more complicated to find our valuable assets stored in specific rooms, vaults, and so on. Let's start with how they would be able to enter in our house. The hacker will try to connect to our public web page using SQL, command line injections, port mapping. They are trying to get as much information, helping them to penetrate the front door by getting the IP, the name of the host, the library used by the application, or simply environment variables or details on the host of our applications. Like I explained, they would also use network tools to get the port exposed by this public address, see if there's any weak encryptions in place or any missing firewall rules. The game is simple. Try to find a door and then connect to it. When working in our environment, we usually connect to our servers using SSH tools, but the hacker clearly expects that we're using private keys or expose SSH ports to a limited number of IP addresses. So it will try to do what we call a reverse connections. So what does it mean? It will launch locally to his laptop tool that will be listening for incoming connections. Then he will try to find a way to ask to our applications to initiate the connection to his laptop. There are tools like PwnCat that will help them to achieve that. So the game is to find a clever way to open a remote connections to our server. Once the connection is done, then we are in our house. To find the valuable assets, the thief will explore our house by going from one room to the other. But in Kubernetes world, based on pods, in fact containers, our house is a bit like a hotel. When connected, the hacker is technically in a pod, a container, so the hacker is in one of the rooms of the hotel. He will try to see if he can open other doors with the current key of our container. So the hacker will try to look at how much information he is able to see using the service account of the container. Or he will try to use command line to get the IP of the hosts, so our nodes, and then from there try to sniff the traffic and get more valuable assets. As you may know, each application uses a service account in the cluster. The service account is linked to a specific role within our cluster. The user account is a bit like the key in our room. In many hotels, the key of a room is often limited to the access to the various floor of the hotel. So the hacker will try to use kubectl with the token of the service account. Usually it could be stored as a simple secret in our cluster. That is really dangerous, by the way. That is why we need to give a limited rights to the service account of our applications. If the service account or the container has limited privileges, the hacker will try to find another pod interacting with our applications. The idea is to find another workload having higher privileges out of the service account. If our application is running under the root account, then we are letting the attacker to install write files by giving the root access to our container. We are clearly helping them in their explorations. They could use extra tools to sniff the traffic of the pod or even the node. He's trying at the end to identify workload that may be more vulnerable. Once he found the right vulnerable pod, he could simply use kubectl with the Kubernetes token again of this vulnerable workload to deploy a pod having higher privileges on the node. And then simply connect to this fresh new pod deployed in the cluster and run command on a node to get information, root passwords, and so on. So what can we learn from this information? First, the application needs to be designed in a secure way, avoiding command line, SQL injections, or any port mapping. Second, if our application is using a vulnerable library, the attacker could take advantage of it to do the similar approach. Third, our workload needs to use restricted RBAC to avoid exploring the entire cluster. 4, we need to limit the privileges of our pod, avoiding giving the attacker higher rights to install extra toolings in our environment or even inspect our node. Last, we need to have policy in place to limit the traffic of our pod, because if no policy in place, the attacker could send traffic to any workload of a cluster. We need, of course, to have policies in place to block strange workload asking for high privileges. So at the end, there are clearly different things that we need to consider when using our application in a Kubernetes cluster. The market classify them into 3 sections. So build our applications, deploy, and of course, runtime to add restrictions and detect vulnerability within our running pods. Because our application is a potential door to our cluster, we need to build secure code and container images. When building our applications, there are different levels of security that we need to consider. Our code needs to be safe to avoid any backdoor to our environments. This piece is pretty much related to code secure applications. To code our application, we often utilize external libraries for logging, writing assets into disks, external storage, database, or even observability. All those external libraries need to be safe and not introduce any weakness in our cluster. So to detect any vulnerability in the build phase, I'm not going to learn you anything. We are going to use scanners that will help us to detect any weakness. So in our CI/CD pipeline, we will scan our code to detect any security weakness. This can be done with a well-known tool called SonarQube. Next step, we will need to build a container image for our applications to deploy it in our cluster. When building our container image, we rely on operating systems, packages that could also introduce weakness. To detect any weakness in our images, we usually start by producing an SBOM file. SBOM stands for Software Bill Materials. This SBOM won't give you any feedback on the vulnerability of a given library, but it is a crucial information because it will give you a picture of all the different parts that makes our software. It is technically the inventory of the library and packages of our applications. What type of information will you get from an SBOM? There are two formats in the industry, SPDX and CycloneDX. Both will provide for each library or package of our software the supplier name, the component name, the version, the dependency, the creator, and even the licensing details. But SBOM files at the end is only the inventory helping to identify any licensing issues. It is not telling us if one of those packages is vulnerable. That is why we usually take the SBOM file with another solution that will download a local database, unknown vulnerability. We usually rely on OSV, open source vulnerability database, that aggregates vulnerabilities of open source components and also other ecosystems like Python, Golang, Rust, GitHub advisory database, global security database. In those databases, every library, packages, components having a vulnerability on a given version would have a CVE number, common vulnerability and exposure. The tool will go through our inventory and lists all the components having a known vulnerability and the criticality of it. There are tools that will produce the SBOM and also lists the vulnerability at the same time. This is the case of, for example, of Trivi. Generating this scan when building our application is great, but it provides some limitation. The tool scans our library and checks if one of them are considered to be vulnerable at the moment of the scans. So you can use a version of the library, scan it, and no vulnerability would be detected. But maybe a few months later, this library is considered to be vulnerable. So we cannot limit ourselves only on the results produced during the build process. It is clearly inefficient because the vulnerability database is changing over time. That is the reason you need to consider continuously scan your image registry to detect any weakness on our existing images. It will be even more productive to include a scan at the runtime in our production environment. The issue of scanning at the build is that it will clearly list a lot of vulnerabilities within our images. Because the scanner is looking at the libraries included in the image, it is not able to understand if this library would be actually loaded when our application is running. That is why runtime scanners are usually more efficient to avoid lots of noise. Runtime scanners capture the exact library used, loaded by the application. It will help us to focus our effort on the vulnerability that could clearly impact our application and users. But one of the biggest challenges is that when building a modern software, we are today relying on many external libraries, and the current state is that the number of vulnerability is continuously growing over time, even if our community is putting a lot of effort to resolve the existing ones. So we need to be aware that we are running risks with few libraries and utilize tools that will mitigate the risks if an attacker is exploiting this vulnerability. To deploy our application, we will need to define the right manifest file, defining how our application would be deployed, and eventually the networking required to expose the application through a Kubernetes service. When building our manifest file, this is where we're going to define the security context of our workload and the service account used by the application. The security context is a critical part of our deployment because By misconfiguring it, we could let our pod having an access to the host network or having root privileges and more. If you pay attention to the objects deployment, stateful set, daemon set, and others, there is an option named security context. The security context can be defined at the various level of our manifest. So at the spec template, there will be assigned a global policy to all the containers of the pod, or a specific security context for each containers. Through the security context, we'll assign the specific user or group, and even the FS group for our volumes. So even if you have built your container with a specific user, the security context can allow you to use another user or group. Like explained, the attacker will try to install extra toolings in our container. So to block the hacker to add libraries in our container, we can force to mount the container root file systems as read-only. Security context is a huge concept with lots of various configurations. We can define the security capabilities where we will control what type of kernel rights we are authorizing, or in the opposite, what kind of kernel rights we are disabling by dropping that capability. For example, so here is a stateful set deployment, and you can see that there is a security context where we are dropping all the capabilities except SUID. But SUID is technically the privilege to set hype rights to the account. So if the attacker reaches this container, which is in fact a process running on the host, he could easily get the host IP and start sniffing the traffic. That is the reason we want to precisely define the right capability. If you're not defining any capabilities, our container will get the default capabilities. So here is the default list of capabilities. With the default capabilities, you can already let the attacker do lots of malicious things, especially cap syssh root, set UID or set the group ID, or even the net bind service. To get the full list of capabilities, look at the following URL. The only challenge is to identify the right kernel capabilities that we need to run our applications properly without any problems. So we should start by dropping all the capabilities and then only add the ones that we really need to limit any security risks. Security contexts are great, but they would be defined by the project team. That could sometimes request for more privileges than the one that we officially authorize in our organizations. So how can we avoid having a workload having high privileges in our cluster? Well, a few months ago, Kubernetes had an interesting feature called pod security policing, allowing us to define the default policies authorized in the cluster. If our deployments were not respecting those policies, then our deployment was rejected by the scheduler. Since Kubernetes 1.25, this feature is deprecated and has been replaced by adding a pod security admission, where we have a pod security standards that we can enable on a given namespace by adding the right annotations. There are technically 3 levels of security standards. So we have privileges, so allowing everything to this type of workload. We have baseline, providing the minimal restrictive policy, basically the default security context that I mentioned before, and restricted, where the pod is having a limited restrictions. The project could only add netbind as a capability. To enable the pod security admission, we would need to add the right labels to our namespaces to define the type of level, but moreover, how to react on the violations of our policy. So there is enforce, means that the workload having a security context not respecting the defined level would be simply rejected. Then we have auditing. If there is a violations, the workload will be allowed, but it will trigger an audit log. And last, we have warning. If there is a violations, a simple warning would be raised when deploying the workload. To set the level and how to react, this is done by defining the following annotations to the namespace. So here you can see that there is pod security kubernetes.io, then we have the mode and the level. So mode meaning enforce, audit, warning, and the level will be privileges, baseline, restricted. Otherwise, there are external tools helping us to build more advanced rules on our security in our cluster. The permissions, the resource usage, the type of users, and more. You can either use OPA Gatekeeper or Kubernetes. Those tools will introduce new CRDs defining our policies, and we basically block any workload not respecting our policies. The other important thing that we've discussed is the service account assigned to our workload. When running application, we will assign a service account. If not, it will use a default one provided by the namespace. Creating the service account is one thing, but defining the actual authorized right is even more important. The role and role binding could be done at the namespace or at the cluster level with cluster role and cluster role binding. Last, most of our sensitive data that we have in Kubernetes, so it could be login, it could be password, it could be certificates, it could be encryption keys. They are usually stored as Kubernetes secret. But we will see later, secrets in Kubernetes are great, but by default, the value would be only base 64 encoding. To secure our Kubernetes secrets, we can enable encryptions on our Kubernetes secrets using encryptions configuration. That will use a specific encryption key to encode our secrets, but the downside is that we will need to store it somewhere secure to be able to encode, decode our values. Again, we are securing something, we're storing it somewhere else. So if the attacker have the access to that key, then it doesn't matter. Otherwise, we can utilize a solution like external secret operator that will connect our cluster to a third-party services in charge of storing our secrets in a secure way, like Amazon Secrets Manager or Google Secrets and many more. The other important thing to consider is the networking. As you know, in Kubernetes, by default, a pod can send a request to any workload of the cluster. And the communication is not encrypted, so we can easily sniff or capture the traffic from one workload to get to the other. Moreover, if you're not limiting the traffic, the attacker can technically send a request to any pod of the cluster to discover more vulnerable workload. So how can we restrict our network in our cluster? Kubernetes provide an object named network policy that can be deployed on each namespaces. With this object, we can determine who is authorized to send the traffic to a given workload. This is done with the ingress rule, and also we will define where this workload can send traffic. So this is with the egress rule. From the network policy object, you can either authorize outside communications by defining authorized port or defining authorized IP address. When it comes to internal communications in our cluster, we can define rules using namespace selector or pod selector or even both. To simplify our configuration journey, ISOViolent has built a web page helping us to configure our network policy. So here is the link to this online editor. Again, one important thing is the Kubernetes rule policy is designed to create rules on the layer 4 of the network based on the address, the IP, and so on. But if you're planning to create more advanced rules on the layer 7, anything related, for example, the URL, the post parameters, the default Kubernetes network policies would be a limitation. This is why there are container runtime interface CNI like Cilium that will manage our network using eBPF and provide new CRD like the Cilium network policy that will support L4 and L7 rules. If you want to learn more about Cilium, check the episode related to it. The other important aspect is the encryption of the network running in our cluster. This can be easily done using a service mesh. I have done several episodes on service meshes, so Istio, Kuma, Linkerd on this channel. So I would recommend to go and look at those videos to understand a bit more how you can enable this. Very important. is to limit the resource usage of our namespace. Why? Well, let's say that we have a front-end service exposed to the outside world through an ingress rule or a service mesh or using gateway API. And let's say that the workload behind has an HPA, so no auto-scaling rules defined. So if an attacker starts running a DDoS attacks, not filtered by an external proxy or any security components, then the DDoS attacks will result in adding more and more and more and more replica. By creating a resource quota, we are putting a gatekeeper to avoid adding too many resources in our cluster during this attack. The DDoS attack could also be managed by using a rate limit rules provided by a service mesh. In the rate limit rule, we can define how many requests can be sent by a given IP address, web sessions, and so on. Once we have security policies in place, we have restricted our network, defined limited permissions, we need tools that will help us to identify suspicious events in our cluster. Again, like mentioned, we may end up running a code in our cluster that could be considered vulnerable after a few months. In that case, it may result into a backdoor to our cluster. In that case, we want to be alerted or even block any suspicious activities. For example, a process that suddenly is trying to have access to the password folder or trying to change privileges of our workload, that seems very suspicious. For that, there are various toolings available in the CNCF landscape. So we have Falco, Tetragon, Kubernetes, and more. Those solutions will rely on the sets of rules that we need to define. Those rules will determine the sets of actions that we would like to block or simply notify us. Last part in the runtime is using runtime scanners that will continuously scan our running applications for known vulnerabilities. Like mentioned previously, we need to be aware that existing code could be vulnerable after a few weeks or few months. The advantage of those solutions is that they are looking at the libraries loaded and used when our users are interacting with our systems. There are plenty of commercial solutions providing that type of support, like Trivi, Dynatrace, and more. When dealing with a vulnerable library, detecting it is one thing, but knowing exactly which user journey is impacted by the vulnerability is even better. Or even more, understand which distribute traces is impacted. This is super powerful, and like usual, we need to collect as much details to share it with our dev team. That's it for today's episode related to how to make your Kubernetes cluster safe. I have not touched on few things, but they sound quite obvious. So on the node itself, no surprise, your node used in your cluster needs to be in a private network. They always need to be updated with a recent kernel version. They need to be behind a firewall, and so on and so forth. We also need, of course, observability. That's why we are watching this episode on Is It Observable? Because at the end, I didn't have the chance to explain how to collect data from those best practices. But keeping continuous track on the security is also an important aspect of our observability journey. So applying security is one thing, but observing our security best practices is even more important. But to briefly summarize what we talked about today, making our cluster safe, we'll go through several steps. So first, our application code needs to be secured by doing some scans on when building the application. We need to build secure images. We need to define the right privileges to our containers using security context or the right kernel capabilities. Avoid using, of course, the root account, that makes sense. But define global policies within your clusters, and there are solutions that will make those policies global easier, like OPA Gatekeeper or Kubernetes. And again, secure network by putting network policies, that makes sense. Add a service mesh to add encryptions or MTLS between the communication within the pods. And if you have any DDoS attacks, put some resource quota on your namespaces, add, for example, a rate limit if you're using a service mesh. That would at least limit the risk. And of course, this is great, but if you're having already an ongoing application that could be vulnerable, we need a solution that detects suspicious activities on the clusters, and that is recommended. So also look at the runtime using solutions like Falco, Tetragon, others. Using runtime scanners will help you to be more efficient in your security journey. This episode is an introduction to a series, so I will soon cover a more specific episode on how to implement those things with Kyverno, Opa Gatekeeper, and others. So if you like this type of series, keep posted. I will release those episodes soon. If you enjoyed today's content, don't forget to like and subscribe to the channel. So see you soon for another episode.